What specific problem does the AT-EDM framework aim to solve in the context of diffusion models, DMs?
The AT-EDM framework aims to solve the specific problem of accelerating the inference process of diffusion models, DMs, at runtime without the need for retraining. This is achieved by leveraging rich information from attention maps to dynamically prune redundant tokens in order to accelerate attention blocks within the model. The framework addresses the issue of slow inference processes in latent diffusion models, LDMs, despite their practicality and affordability for normal users. By proposing a training-free architectural compression method, AT-EDM aims to enhance the efficiency of DMs without the need for retraining the model backbone, which can be time-consuming and costly. The framework focuses on accelerating the inference of pre-trained DMs by identifying and pruning redundant tokens in attention blocks, thereby reducing the computation cost and memory footprint for each denoising step.
How does the proposed AT-EDM framework work in accelerating pre-trained DMs without retraining? Illustrate step by step.
The proposed AT-EDM framework accelerates pre-trained diffusion models, DMs, without retraining through a multi-step process. Firstly, attention maps are obtained from an attention layer in the U-net, either from self-attention or cross-attention, and a scoring module assigns importance to each token based on the attention map using the Generalized Weighted Page Rank (GWPR) algorithm. This algorithm iteratively determines the importance of tokens based on the attention map until convergence. Pruning masks are then generated based on the calculated importance distribution, and tokens with lower importance are pruned using the generated mask after the feed-forward layer of attention layers. Tokens are pruned in each consecutive attention layer, except for the last attention layer before the ResNet layer. To maintain image quality, a similarity-based token copy approach is used to recover pruned tokens by copying tokens from retained ones based on their similarity. Additionally, a denoising steps-aware pruning (DSAP) schedule is implemented, which prunes fewer tokens in early denoising steps where attention maps are less informative and more chaotic, and more tokens in later denoising steps where attention maps are more informative and can better differentiate unimportant tokens. This schedule involves leaving specific attention blocks unpruned in the up-sampling and down-sampling stages to enhance image quality. The DSAP schedule is determined through ablation experiments and is compatible with any token pruning scheme, providing a comprehensive approach to accelerating pre-trained DMs without the need for retraining.
What are the advantages of using the GWPR algorithm for token pruning in a single denoising step within the AT-EDM framework?
The advantages of using the GWPR algorithm for token pruning in a single denoising step within the AT-EDM framework are as follows. 1. Efficient token pruning. The GWPR algorithm efficiently assigns importance scores to tokens based on attention maps, allowing for precise identification of redundant tokens in each denoising step. 2. Dynamic pruning. By dynamically pruning redundant tokens, the GWPR algorithm accelerates attention blocks in the model, leading to faster inference without compromising image quality. 3. Compatibility. The GWPR algorithm is compatible with both self-attention and cross-attention, making it versatile and suitable for different types of attention mechanisms used in the model. 4. Improved image quality. The GWPR algorithm helps maintain high image quality by ensuring that important tokens are retained while removing redundant ones, resulting in clearer objects with sharper details and better text-image alignment. 5. Algorithm design. The GWPR algorithm is designed to map the importance of query tokens to key tokens, ensuring that tokens crucial for image generation are preserved, thus enhancing the overall performance of the diffusion model. 6. Complexity. With an OMN complexity, where M and N are the number of query and key tokens respectively, the GWPR algorithm efficiently prunes tokens without significantly increasing computational overhead. 7. Token recovery. The GWPR algorithm facilitates token recovery by identifying and copying similar tokens to fill in the pruned areas, ensuring that the generated images maintain high fidelity and quality. 8. Enhanced efficiency. By utilizing the GWPR algorithm for token pruning, the AT-EDM framework achieves significant flops reduction, 40%, relative to the full-size SD/XL model while maintaining state-of-the-art results in terms of image generation performance. 9. Run-time acceleration. The GWPR algorithm contributes to run-time acceleration without the need for retraining, making the inference process faster and more practical for normal users. 10. Wide applicability. The GWPR algorithm's effectiveness in identifying redundant tokens and accelerating attention blocks makes it a valuable component of the AT-EDM framework, demonstrating its wide applicability and benefits in enhancing the efficiency of diffusion models.
How does the proposed DSAP schedule in the AT-EDM framework deal with the variance of attention maps across denoising steps?
The proposed DSAP schedule in the AT-EDM framework addresses the variance of attention maps across denoising steps by adjusting the pruning ratios based on the importance of each denoising step. The schedule recognizes that early denoising steps have more chaotic and less informative attention maps with low variance, indicating a weaker ability to differentiate unimportant tokens. In contrast, late denoising steps yield more informative attention maps with higher variance, better distinguishing unimportant tokens. To leverage this insight, DSAP implements a prune, less schedule in early denoising steps by leaving certain attention blocks unpruned. Specifically, it selects attention blocks in the up-sampling and down-sampling stages to remain unpruned, as they contribute significantly to image quality. By strategically choosing which attention blocks to skip token pruning in, DSAP enhances the efficiency of the denoising process and improves the overall image quality by accurately identifying and retaining important tokens while pruning redundant ones. This approach optimizes the pruning strategy across different denoising time steps, leading to clearer objects, sharper details, and better text-image alignment, ultimately enhancing the performance of the AT-EDM framework.
What results were achieved in the quantitative evaluations comparing AT-EDM and TOM on SD/XL, particularly in terms of FID and clip scores under various flops budgets?
In the quantitative evaluations comparing AT-EDM and TOM on SD/XL under various flops budgets, AT-EDM achieved better image quality than TOM with lower FID scores across all flops budgets. Specifically, when the flops budget was extremely low, less than 50% of the full model, TOM achieved higher clip scores than AT-EDM. However, when the flops saving was in the range of 30 to 40%, AT-EDM not only achieved better image quality with lower FID scores, but also demonstrated superior text-image alignment with higher clip scores compared to TOM. Under the same CFG scale, AT-EDM achieved a lower FID score than the full-size model while reducing flops by 32.8%. Additionally, when trading text-image alignment for image quality by reducing the CFG scale to 4.0, AT-EDM achieved both a lower FID score and a higher clip score than the full-size model while still reducing flops by 32.8%. These results demonstrate the effectiveness of AT-EDM in improving image quality and text-image alignment compared to TOM across various flops budgets on SD/XL.
What are the limitations or drawbacks of the proposed AT-EDM framework based on the experimental results and analysis provided in the paper?
The limitations or drawbacks of the proposed AT-EDM framework based on the experimental results and analysis provided in the paper include the potential trade-off between image quality and text-image alignment. When the flops budget is extremely low, less than 50% of the full model, TOM achieves higher clip scores than AT-EDM, indicating that AT-EDM may sacrifice text-image alignment for image quality under very stringent computational constraints. Additionally, the latency analysis shows that deploying pruning at the second feature level may exceed the latency reduction it leads to, making AT-EDM slower in certain scenarios. Furthermore, the DSAP schedule, while effective in improving image quality, may require careful tuning of parameters such as the number of early prune, less denoising steps to achieve optimal results, which could be considered a drawback in terms of ease of implementation and generalizability. Lastly, the need for additional calculations of attention maps in the current implementation of X-formers to support the AT-EDM framework may introduce extra computational overhead, impacting the overall efficiency of the framework.